But basically, this is telling you, whenever we have dielectrics, we apply external field. We induce electric dipoles, and the induced dipoles effectively give you, for homogeneous material, they give you polarization, surface charge densities, simply P dot AN, the surface normal. And if you have inhomogeneous material, those induced electric dipoles end up giving you effectively some volume charge density, negative divergence of P. From our understanding to Coulomb's law or Gauss's law, whenever you have non-zero charge distribution, those charge distribution creates its own field distribution, right? So you're free to replace all these charges, right, into Coulomb's law formulation or Gauss's law formulation. So this is telling you, once you have induced electric dipoles, they create their own field distributions. So you need to calculate them. And that's making things more complicated, right? You must be thinking, oh, I have externally applied field, which I need to calculate, and I have material, I have to calculate everything, because once I have induced dipoles, I have to calculate their resulting field distribution. That's very tedious. And you want to drop this class. I can imagine your frustration, but in the upcoming slide, I'm going to tell you things are not so complicated. We're smart, right? We can find a way to quantify dielectric materials in a very simple sense. Alright, so bear with me. And this is the point why we want to define a new vector field quantity, flux density, capitalized D. Okay? And it only makes sense to talk about D whenever you have materials. For vacuum, you don't really care. You only care about E, the electric field intensity. But once you have materials, we talk about is D. Okay? I am going to define D, but I want to make a discussion which makes more physical sense. The meaning of flux density and the difference as compared to electric field intensity. Okay? So let's come back to the very first fundamental postulate when we talked about E field intensity. So we first talked about the divergence of E is equal to rho divided by epsilon 0, right? Initially, we didn't talk about what type of charge density was related to E. But now I'm telling you, when we are in free space, right, we're in free space, in vacuum. Vacuum is defined as nothing, right? So if you want to create some field distribution in vacuum, that has to come from free charges. This is the best way for you to remember it and understand it, right? Vacuum has nothing. So if you can create some field line, it's definitely coming from free charges. So divergence of E in free space is basically coming from free charge densities. Okay, free. But now we're talking about materials, and especially dielectric materials. Whenever you have matter, you have atoms, you have molecules, you have the ability to create induced dipoles, right? So in this case, when we're talking about dielectric medium, divergence of E is no longer just comprised of the free charge densities, but we also need to take account of the charge densities created by the polarization factors. Okay? Remember, we spent so much time talking about what the electric dipoles do. They provide additional charge densities. And we now know how to formulate these charge densities. So inside the material, you need to add the polarization-induced densities, charge densities, to the free charge densities. Right? So basically, when we're talking about matter, dielectrics, divergence of E is rho total, the total charge densities divided by epsilon 0. Okay? So another way for you to remember is, this is the real generalized expression. But when you are going into free space, you have no way to induce electric dipoles. So rho p is always 0 for vacuum, and therefore you have the first fundamental postulate. Okay? But now that we know from the previous page, rho p is equal to negative divergence of polarization factor. Okay? So now we have one divergence and we have a second divergence. Why not combine the divergence to one side to make everything simple? We can do that. We can only multiply this epsilon 0. It's a constant. We can just multiply it to the left-hand side. And divergence is distributive. We can combine these two into the divergence, right? So now it reads divergence of epsilon 0 E factor plus P factor is equal to rho free. So why not define the sum of these two vectors as a new vector? So it's easier for you to write. So why don't we define this D, a new vector field, as epsilon 0 E vector plus P vector? So you don't have to write so many things. Okay? Now, by this definition, divergence of D, this D is called the flux density. The electric flux density is a vector. It's equal to rho free. So at this moment, think hard. I mean, what's the difference between D and E? What's the difference? While you're thinking very hard, let me just try to write it for you. So divergence of D is equal to rho free. On the other hand, divergence of E is equal to, use another color, rho net divided by the constant. these two formulas is telling you this D vector is directly associated only with the free charge densities. Like you have free charges in space. So inside the material, this D is related to only the free charge, but E is related to the total charge. Okay? This net charge is the sum of free charge density plus the polarization charge density. Right? Now, before I go on, take a guess on which field quantity can be smaller. Take a good guess. And if I only care about the amplitude of D as compared to the amplitude of E, if I don't care about this constant, which one can be smaller? When I was a student, I looked at this definition, and because if I don't care about epsilon 0, rho free plus rho p, right? My instinct was to say, well, because the net charge density is the sum of the free charge density, this guy, plus some additional value, the polarization charge density. So this adds up to a larger value. So initially I assume if I don't care about epsilon 0, okay? If I don't care about epsilon 0. It seems this mathematical formula can be misleading. Because you think, oh, you add additional charge densities. So this guy is stronger. Is that true? We can skip this. Okay? We can skip this one. Let's come back to the picture. Remember, as I talked over and over, repeatedly, we have a given dielectric material within this black lines, and we apply external fields. You can imagine the externally applied field is the result of free charges, right? Because in vacuum, you want to create field, you have to have free charges. And these free charges create the externally applied field lines, and they induce electric dipoles inside the material. And as we talked about, whenever we have induced dipoles along the surface, we create induced surface charge densities, assuming this is a homogeneous material. So now we count the number of charges for this surface. Initially, I have 8 positive free charges, but now I have induced dipoles, so I have to subtract 3 negative charge. So basically, rho free plus rho p is reduced. This is actually a reduced amount of charge. It's also true here for the bottom surface. Initially, I have 8 negative charges, but somehow due to the existence of the induced electric dipole, I have 3 positive charges on the bottom surface. So these adds up to a smaller absolute value quantity. This is in perfect accordance to the fact the field lines generated by the dipole is used to counteract the externally applied field. Okay? So don't be fooled by this plus sign. You are actually adding a negative quantity. Alright? So in the end, E is related to the net charge density. So you only have, 5 net charges on the top surface. So basically, try to remember and try to understand. I repeat, dielectric materials give rise to induced electric dipoles for only one purpose. They want to make the field strength inside the material weaker as compared to your externally applied field. So this E absolute value is smaller than D. Okay, we don't care about this constant, okay, for now. Induced dipoles are there to make the field strength inside the material weaker. So do not be fooled by this plus sign. Okay? Because this plus, if you have positive free charge, you are adding a negative charge density, effectively making E smaller, weaker. Alright? Okay, so the better way, the very simple way, now that we know this phenomenon from a pictorial way, so now it's math. We can somehow formulate, well, because we know that the dipoles are aligned in the direction of my externally applied field. So somehow P, the vector, the polarization vector, is also aligned to my external field, right? And then we have some scaling. So depending on different material, this chi is called the electric susceptibility, chi E. How good is this material capable of giving rise to electric dipoles? If you have a very high chi E value for a given material, this material is very sensitive. So you apply some external field, it produces a lot of dipoles. Right? Vacuum has 0 chi E because vacuum has nothing. You cannot contribute to electric dipoles. Right? So in another sense, metal has a very huge chi E. It's almost infinite, right? So now, we have P equals epsilon 0 chi E times the E, external field, right? We can just replace this P by epsilon 0 chi E. So basically, the flux density, which is associated to free charge density, can now be formulated as epsilon 0, 1 plus chi E times the E vector. And we call this 1 plus chi E as the relative permittivity of that given dielectric material. Right? So this is very easy. For any given material, somebody measured its capability of generating induced electric dipole, and that is coined or quantified by this chi E value. Or together, 1 plus chi E is this relative permittivity. For example, for water, chi relative H2O is 1.33 squared. Epsilon r, glass, is 1.5 roughly squared. Okay? So in the future, I mean, you only look for this relative permittivity, and you can just calculate, or you can understand, you can classify the material response. Okay? So all dielectric responses are somehow represented fully by this relative permittivity. It's a constant. Once you know its operational frequency, it's just one constant. So you no longer need to take care of all these and not even this. Okay? You don't really need to calculate the field distribution or potential distribution due to the induced charge densities. Everything is represented by that simple constant. Okay. Well, sometimes people try to combine epsilon 0 times epsilon r, and we define it as the absolute permittivity. Okay. So basically, d equals epsilon 0 times epsilon r e. But sometimes you're even lazier than that. You want to combine epsilon 0 times epsilon r as one single variable, epsilon, and that single epsilon is called the absolute permittivity. Okay? Now, again, the very last minute, the most important message of wisdom. D equals epsilon E. Again, this is a confusing formula. When I was a student, I thought, oh, if I have a material with very high epsilon value, a very high epsilon value means what? Means this material is very capable of generating induced electric dipoles, right? So I thought, oh, if I have a material with very high epsilon, that is making its D very big. Is it right? Think about it. Is it right? D is only related to the free charge density. So even though you have different materials positioned in space with the same applied external field, D remains to be a constant. Okay? So my suggestion for you is try to remember this relation between D and E in a different way. This expression, E vector, is a flux density vector divided by epsilon. This is making more physical sense. It's the same equation written in a different way, but now this is telling you there's no room for ambiguity. If you have a material with very high epsilon value, it's making your field strength in terms of E field intensity, which is associated with the net charge density, to be weak, right? So this writing formulation is telling you D should be held as a constant because it's only related to free charge density. E is related to the net charge density. So the difference is, for different material, you have different ability to form induced dipoles. If you have a material very capable of producing induced charge density, induced dipoles, then you have a very high epsilon value. And the sole purpose to have induced electric dipole is to counteract your externally applied field, and therefore making the E intensity weak, right? So this is a more proper way to write down this formulation. Very high epsilon, you have lots and lots of electric dipoles, and making your resulting E field intensity weak. So one final test to your understanding. If I use this formula and I want to describe metal, what should the epsilon value for metal be? Inside the metal, you have no E field intensity. So this, in terms of this absolute value for metal, epsilon reaches infinity, right? And that is in accordance to our understanding. Metal is a material for perfect induced electric dipoles. All right, so let's conclude here.